to introduce first John Naliboff and thank John Naliboff and all of our mentors for participating in our inaugural SMOREs program. John was a leader and one of the chief motivators for this program. So I'm going to hand it off to him to introduce to you the program and our speakers for today.
Excellent. Thanks, Lorraine. Can everyone see this? Excellent. Great. Well, welcome everyone, and thank you, Lorraine, for the nice introduction. This webinar is summarizing the first pilot CIG Summer Modeling Research Experiences program. And the key focus of today will just be to allow the students to present their work over the course of the program. And so a very quick overview of the program before we get to the student presentations. The motivation for the program was originally that two things. Members of the geodynamics community come from a broad range of communities, but many of these are the least diverse in the STEM fields. And also too few undergrads with proper numerical and computational backgrounds are available for recruiting into the geodynamics community. So the challenge and the chief motivation for the program was to simultaneously increase computational competency among students and then also the diversity in the student population we're recruiting into the geodynamics community. So the solution for this, and sort of in the broad sort of theme of the NSF REU program, was to provide funded undergrad training and research opportunities, and in this case specifically target underrepresented groups in our advertising for the program. So before we say a few more words about the program, I think it's important to acknowledge everyone involved. First, we'd like to thank NSF for supporting CIG and for providing initial guidance on this program as we laid it out over a year ago. Special thanks to CIG Director Lorraine Wrong for who funded, supported, helped conceive, and then organize the program. Also, Dave Stegman, who was very influential in helping us think about the organization of the program and also providing advice from prior REU activities he had run. Two more acknowledgements. Next, I'd like to acknowledge the CIG Science Steering Committee members, Sylvain Barbeau, Krista Sutherland, and Kean Wilson, who reviewed all of the applications, which totaled close to 40 for the program. And then last, of course, thank you to the participants, the mentors, and the students. So a very quick note on the participants, both students and mentors. There were over 35 applications for the program. The students selected for the program were Elena Ehrlich from North Carolina State, Keneni Godana from University of Illinois at Chicago, Dante Reed from Reed College, Hiva Mohammadzadeh from Pierce College, and who's now at UC Berkeley, and Brady Okongwo from UC Santa Barbara. Our mentors included Magali Billen, Katie Cooper, Eric Mittelstad, myself, Max Rudolph, Joy Shim, Suzanne Schmecker, Dave Segman, Laura Waters, and Yolanta Van Wyck. And you'll notice that there are more mentors than students in this case. And the idea we had in the program, which we thought worked very effectively, was rather than have a student assigned to a single mentor, we actually had teams of mentors working with each student, and in some cases more than two, and that turned out to be extremely effective. So the way the program structure worked, and we're going to revisit this in thinking about future programs, is the following. Of course, due to COVID, the program was unfortunately largely virtual, but overall it was still quite effective, and that we were able to make things run both in the training and the research programs in effectively an entirely virtual environment. The program began with 2 weeks of virtual tutorials. This covered everything from the basics of Python and coding to reviews of geodynamic processes to actual geodynamic modeling. And so short courses on geodynamic modeling. After that, we had 6 to 8 weeks of research projects. And then the research projects, as you're going to hear later today, they focus on anything from mantle convection to melt and volatile transport, magmatic processes in the lithosphere to sort of long-term tectonics. And then through the course of the research projects, what we also made sure to do, because we weren't able to have live interactions, is we did cohort building through weekly group meetings. And this covered anything from individual project updates to tips for grad school applications and a range of other subjects. So now, without further ado, what we'd like to do is go straight to the presentations. And we're going to begin with Dante Hickey from Reed College. So Dante, what I'm going to do is I'm going to stop sharing my screen, and feel free to go ahead and share from your end.
Does that look all good? You can hear me?
Yep, it looks great, Dante.
All right. Great. Okay, so hello, my name is Dante Hickey. Today I'll be talking about my SMOREs 2021 research project. As above, so below, a simulation of the Continental, Lithospheric, and LLSVPS as thermal insulators using aspect. I worked on this project with my two mentors, Dr. Kathleen Cooper from Washington State University and Dr. Ehrlich Middlestead from the University of Idaho. I'd like to start off by sharing a bit about who I am and my background in computational geodynamics. I'm currently a senior physics major at Reed College in Portland, Oregon. And prior to this project, I had a little bit of experience in programming in Python and Unix, and some knowledge of geoscience from hobbies and college classes, but not a lot in either. So to make sure we are all on the same page, I want to go over some information that will be helpful in understanding our project. The first topic I want to talk about is heat flux. Heat flux is the vector quantity of heat flow per unit area per unit of time, usually quantified in watts per meter squared. We're looking at heat flux because it's an important quantity for us to, because it helps us better understand planetary cooling and interior processes such as melt. A factor to consider when determining heat flux is the existence of thermal insulators, which show the rate of energy transfer. And so getting into like what this project's about, for this project, we were looking at two of the Earth's biggest thermal insulators, the Continental Lithosphere and LLSVPS. The Continental Lithosphere makes up the rigid outermost layer of the Earth and has been shown to act as an insulator for the Earth. Other insulator we are interested in are the LLSVPS, or large low shear velocity provinces. It's piles of anomalous material that were discovered in the 1980s using seismic activity. They are located deep within the Earth's interior in the lower mantle along the core mantle boundary. This image on the left shows the two LLSVPs, shows a slice of the Earth. And then we have the Continental Lithospheres on the outer edge. Okay, so as I mentioned before, for this project, we were interested in better understanding how the presence of both these insulating bodies acts as insulators for the cooling Earth. To achieve this goal, we used aspect to perform simulations of Earth's convection with these bodies present in varying amounts over a billion years. And then because of the computational challenge, we used Stampede 2 cluster at the University of Texas to run our simulations. Okay, so we started this project by determining our model properties and building our simulation model. First, we determined the geometry of our model. On the right is an image of the final geometry we ended up using, two-dimensional spherical cell, or an annulus. On the left is a table of the material properties we determined based off our research into lithosphere and LLSVP stability. And so, yeah, for stability, we discovered that we wanted around 3 orders of magnitude greater than the background mantle for our insulating bodies. Another property of the simulation we needed to choose was the refinement level, or the number of individual cells that would be active in our model. After some initial test runs, we decided to use a global refinement of 7, which corresponds with 196,608 active cells. This decision was made by weighing computation time versus accuracy, and found that the accuracy gain from another level of refinement was not worth the significant time increase. So at this point, we were about ready to get our initial results, but we noticed that the bodies were deforming rapidly in simulations. This video on the left shows this deformation. Almost immediately, the continental lithosphere splits apart and mixes with the background mantle. When we look closer at the viscosity of the cells, as shown on the right picture, we noticed that there were some spots of lower viscosity within the material instead of a soft boundary between the mantle and the insulating body. And so to help remedy this and get a better solution, we decided to use particles to track the movement of material rather than computational fields. At the start of this project, we had initially decided not to use particles because of the increased computational time. They now seem necessary to move on. So to start using particles, we updated to the latest software versions of DL2 and Aspect. And after consulting Dr. Nalaboff and Dr. Rudolph, we were able to begin using particles. After switching to particles, we saw better solutions with the rapid deformation issue gone. Still did not see the soft boundary we wanted, as shown in these 3 images of the first 3 time steps. Additionally, we ran into convergence failures when running some configurations. Unsure what the problem was, we tried to change some of the particle properties, such as the interpolation scheme, number of particles, and particle generation. It helped a bit, but still didn't fully remedy the problem. We initially suspected the issue was due to an aspect of the particles usage, but after looking into the issue further, we eliminated the possibility that it was related to the particles themselves. One clue we had was that the density, the other property that was being tracked by the particles making up the insulator, was acting as desired. So looking into the parameter.plm file, which has all of the properties of simulation present, even the ones that are like set by default and we didn't specifically put, we noticed that the viscosity was being averaged harmonically while the density was being averaged arithmetically. After changing the viscosity averaging scheme, we saw better results as we wanted. So even though we had a soft boundary now, we ran into another issue. The lithosphere was thinning and spreading, which we didn't want because that led to unpredictability and not the amount of insulator present that we desired. We determined that this was likely due to high initial temperatures at the start of the simulation before it reaches a steady state. We noticed that the LLSVPs remained intact mostly, probably due to them, their location relative to the temperature. We tried to increase the viscosity of the continental lithosphere by an order of magnitude to 10 to the 25 Pascal seconds, which, as shown on the right, seems to have created a stable insulating body as we desired. Sadly, solving all of the issues that occurred delayed us for too long, and we have not been able to finish running simulations with stable insulated bodies present yet. I am excited to say, though, that I am going to continue working on this project for my senior thesis at Weed College with my 2 mentors, Dr. Cooper and Dr. Middlestead. So if anyone is interested in the results, stay tuned. So to begin concluding my presentation, I want to mention a couple of ideas for possible ways we could extend this project, some of which we may be able to incorporate during my thesis project. We could use more realistic and complex rheology. We could try to increase the range of insulation, have more of one insulating body present and less of the other, or try to simulate other planets to compare to the heat flux of Earth with those. Although we haven't gotten final results yet, with the context of this project as part of the SMOREs internship, I am pretty happy with the results so far. I have learned a lot. I've learned how to build a model in Aspect, how to navigate a remote cluster using the command line, how to update and install software on a cluster, how to perform data manipulation to make graphs, how to view models and pair view, how to make movies from those models, how to troubleshoot on the CIG forum, and how to present, well, and now how to present results. With that said, I want to say a big thank you to my mentors, Dr. Coop and Dr. Middlestead, for all of their help and for agreeing to continue working on this project with me. Thank you to the rest of the SMOREs mentors and mentees for their help along the way, and CIG for organizing and funding this experience. Thank you all for joining today to listen to my presentation as well.
Excellent. Thank you, Dante. Hey, well done. And so in the interest of time, we're going to move on to the next presentation. But if you have specific questions for Dante, you'll be able to have a chance to ask him after all the presentations are done. But in the meantime, feel free to ask questions in the chat. So Kenny, you're up next.
Can everyone hear me okay?
Yes, we can hear you, but the volume is a bit low. Oh.
Is this better?
It is.
Okay, perfect. Hello, everyone. My name is Keneni Godana, and I am privileged of working with Dr. Joyce Sim this summer on looking into the influence of radiogenic heating and its effects on mid-ocean ridge depth and seafloor subsidence. So just a little bit more background and motivations for this project. Mantle convection was more vigorous in early Earth, as indicated by higher Rayleigh number. And there is also a vibrant, like, deep sea biosphere, and it's often referred to as like the origin of life, and it's most likely the place where those microbes and bacteria most likely formed. And there was a paper back in January 2021 by Rosas and Kuranaga that suggested that there is another possible location for these microbes to form, similar to that same aquatic environment, but instead it's like a warm pool by like a volcano or some other type of heating source. But for that to happen, there would need to be some type of exposed land or seamount available for that aquatic environment to be to form. And they suggested that radiogenic material in the Lithospheric could have exposed that topography from seafloor up to the surface. And you can see in these figures how it relates from like present day Earth to early day Earth, or to early Earth. And you can see the seafloor shallowing pushes these seamounts up to the surface, or potentially pushes these seamounts up to the surface for those bacteria to form, as opposed to during modern times where that radiogenic heating strong enough to do that. So I used their plate cooling model from their paper, which I put in the bottom of this slide to just kind of visualize what we were looking at. So the main variable that we were taking into account was something called H*, which is the heat generation unit, which is basically just how much radiogenic heating was available for like each time period. And something else we put into our model, which was all done on MATLAB, was surface velocity. And it was just the average meter per year that the mid-ocean ridges were spreading, and just how fast the material was moving from like inside the Earth up to the surface. And every other variable was kept constant. But these were the things that we were considering, that we first calculated just like a half space cooling model without taking into account that radiogenic heating just yet. And we used that H* value with something called TC, which is when that radiogenic heating starts to affect substance, in order to measure just how much change there was within subsidence throughout time. And I included this to show how the function compared to other half-space cooling models. This is just like the regular half-space cooling model from the Rosas and Coranaga paper is this black line on the bottom. And you can see just like the influence of H star on those subsidence values. So as you increase the radiogenic heating, you can see that over time, it doesn't level out or keep deepening, but instead it goes back up and starts to have like more of a positive change. And I wanted to include some other half-space cooling models for reference as well. So there's the Hastrock cooling model from his like 2013 paper, which shows kind of like the same trend of like it goes down over time and then levels out eventually. And the same thing with the Stein and Stein plate cooling model from their 92 paper. So you can see that like significant difference between the two. So that higher H star value is going to have a higher chance of having that subsidence have a significant enough change to expose that topography on the seafloor. And since this was done on MATLAB, I unfortunately didn't have any like physical, like a, I'm so sorry, like a whole Earth model representation of what we were looking at, but I wanted to include some type of 3D model to show kind of like what the concepts we were looking at. So this is the concept we're looking at for the Hadean eon. So there is zero continent availability, and you can see that there is more vigorous mantle convection. Things are moving pretty quickly. And for the Archean model, things are a little bit less vigorous, but there is 10% continent availability. And we implemented the same continent availability into our model as well. So we did 3 models in total, same thing with the Hadean, the Archean, and for the modern model, we had a 30% continent. And this is the main concept that we were looking at too, with we took into account how much continent was available for the time period, and then looking at how much radiogenic heating was available to see how much change there would be specifically for early Earth. And then we calculated the ocean basin to that, and then filled those basins with modern day ocean volume for all 3 models. And then we calculated mid-ocean ridge depths from there. Yeah, so these are our results. And as you can see, there is a couple of different stories being told here. And it largely depends on surface velocity. So as you can see in this first picture, or first graph, depending on how you view surface velocity over time, there is either a large change between sea level or no change at all. So if we look at it from the view of the Rosas and Coranaga paper, they suggested that surface velocity has not changed much throughout time. So they're looking at pretty much these points right here specifically, where for the Hadean era, or for the Hadean eon, things are pretty close to the surface. So you can see that there is a pretty large possibility that those seamounts could have been exposed. And then over time, things start to reach those same mid-ocean or sea levels that we see today. But if we look at it from a different lens with surface velocity changing over time, you can see that things most likely were staying at simply a same sea level throughout Earth's history. From the Hadean to the Archean to modern times, things stayed around 2000, or give or take, yeah, throughout Earth's history. And same thing with the subsidence versus age. The colors represent the same surface velocity as the first graph. So as you can see here, that same small difference between the surface and then how close the seafloor was to it. So once again, a large possibility that those seamounts could have been exposed, and that decreases over time, versus looking at it through that other lens with things staying pretty stable. And this is that same graph, but compared to my supervisor's graph that she had done in 2016. And This model did not include radiogenic heating, but it kind of tells that same story of like surface velocity was changing throughout time. So things were staying constant with, yeah, give or take, however much we can know from early Earth. So I just wanted to include this to see, or just to show like how much there is like a varying concepts being thrown around as to what could have been happening during early Earth. Yeah. And as for my conclusions, mid-ocean ridge depths for early Earth heavily depended on surface velocity, as I said before. So there is a possibility that those seamounts could have been exposed, but it really depends on how surface velocity was functioning throughout Earth's history. So for future research, I would love to constrain how that was functioning throughout time, as well as how the radiogenic heating itself was functioning too, just to kind of constrain how things were moving and to help yeah, constrain if those seamounts actually could have been exposed to begin with. And these are my citations, and I just wanted to thank my mentor, Dr. Shidra Sim, for being an incredible supervisor throughout this project, and to thank SMOREs for the opportunity, as well as the grants funding this opportunity. Thank you so much for listening.
Wonderful. Thank you, Kenny. Really nice job. The next person up is going to be Hiva. But again, I will remind everyone in the audience that if you have questions for either Dante or Kenny, please feel free to ask them in the chat. But then there will be an opportunity at the end of all the presentations to ask direct questions. Thank you again, Kenny. And Hiva, as soon as you're ready.
Hi everyone, I'm Hiva Mohammadzadeh, and I'm a student, an undergrad at UC Berkeley. And I worked with Professor Dave Stegman from UC San Diego and Dr. Susan Samarkar from NASA JPL. And I worked on interactions between subduction on Mantle, Plumes, and Venus. So I want to start with what we know about Venus already. So we know that it has similar size and density as Earth, and similar heat budget to Earth. But it's an old planet, about 4.5 billion years old, but it has a young surface, which makes us question why it might have subduction happening on its surface. So surface of the Venus actually exhibits clear evidence of large-scale interior constructive motion, but without plate tectonics. So we question why and how that's possible. So there's a hypothesis that it might be a rollback subduction. And as we see here, Earth has, so we see, when we look at the surface of Venus, we see many possible subduction sites. So we see the rift zones, which are these dark lines that look like ridges, and where the lithosphere is thin. And we see also upwellings, which are plumes. And we see that it has a hole, which could be a potential site of subduction. So these two images are topographical profiles of Earth and Venus. So on the left is a confirmed subduction case on Earth. And on the right, it's a topography of Venus, where it looks similar to the left one. So we see that both display normal faulting parallel to the strike of the order trench walls, and that they both have outer rise indicating an elastic flexure. And they both have trench subducting plate rolling back. So in Earth, we see that it's rolling this way. And for Venus, we see that it's rolling this way. So we see that they're both rolling in the same direction. So it tells us that rollback subduction happens on Venus and Earth at about the same scale. And we see on these graphs of topography versus distance, a good correlation between the locations of faults on the outer trench walls and analytical predictions of high surface stresses due to plate flexures. So we see that faulting at these locations on Venus is consistent with the large outer rise values, which indicate partial to complete failure of the lithosphere atmosphere. And these lowest points, it shows that the subducting trench, it's a subducting trench, which shows that the strong plate is bending. And these graphs, they show that both Venus and Earth have similar magnitudes for elastic thickness. So based on these similarities between Venus and Earth, we're gonna find a range of conditions where subduction could happen on Venus and how adding a plume may assist in that. So this project will use numerical models of Mantle convention to examine this relationship. And we will be implementing the SAG-YY code, and the parameters that will be varying are 20 kilometers and 30 kilometers crust and range of different radius and location values for our plume. So our model setup is a two-dimensional slice-through sphere, which we model to be Venus. So it has 30-kilometer crust and 1700 Kelvin, which corresponds to the hot surface of the planet Venus. And our reference viscosity will be e to the 20 pascals seconds, and maximum viscosity will be e to the 24 pascals seconds. Sorry. And so Venus is a stagnant lit planet, so it's strong. It's a one strong big plate, but it has a little gap in the middle, which will be a weak spot in the lithosphere. And it has strong high viscosity around it and low viscosity in the gap. So these models that we had, they don't subduct for a very long time because of its thick surface and lithosphere. So like after 6 million years, the lithosphere thickness of 250 kilometers and 30 kilometer crust, and it's a stable thick crust. So our goal would be to, in these models that takes a very long time for them to subduct, we would want to examine if adding a mantle plume, like a buoyant blob, would initiate in the gap, would initiate subduction on these stable lithospheric models, and fast track subduction on models that were subducting for a very long time. So I went into the code SAG-YY and implemented a new feature, a blob. And so this is a feature that would control the depth of the plume. And this is a feature that would control the radius of the plume in meters. And so I implemented these codes, and we used Stampede to run them. We used the supercomputer Stampede to run them and then look at the results using MATLAB. So looking at the initial conditions, I made a plume that was 400 kilometers radius at 1,000 kilometers depth. So we look like this, and running that model for 48 hours would show us this result. And this is a 20 kilometer thick crust and 400 kilometers radius plume. So we can see that the plume is rising up and going into the gap and fast tracking the subduction very much. So looking at that result versus the result that we had without any plume, we see that it definitely, having a plume definitely fast-track the subduction in this model. These are both at 2.04 million years, but this one that had the plume has subducted very much already. So we tried changing the size of the plume and seeing if that would change the subduction time. And we see that the 300, 400, and 500, so increasing the size of the plume definitely increased the subduction, because all of these are the same amount of time, 1.6 million years, but this one that has 500 kilometers has definitely initiated subduction more than the 300 kilometer one. But for the 500 kilometer plume, we can see that some of the plume material goes underneath the slab and is somehow preventing it from subducting. So we thought, what about we try to move it to the side, to the right by 485 kilometers. So we did that, and we found out that changing the location of the plume changes the dynamic, and it actually fast-tracked our subduction. So this one, it started at 500 and at the center. So we see that this one like rises up and it interacts with the sinking slab. But this one, which just rises up and slides into the gap, it does not interact with the slab. So therefore it will fast track subduction. And we tried changing, we tried moving the plume for the 400 kilometer radius plumes as well. But we saw that even though the plume that was in the center, it's a little, it's preventing the slab from sinking just a little, and it's interacting with it. It's still giving us more subduction as this one. This one is 1.75, this one is 1.78 million years. And we see that this one clearly has given us more subduction than this one. So some conclusions would be that running the model on, so the plume, adding a plume in the gap has definitely increased the time, has definitely decreased the time of subduction, and has definitely assisted the subduction, and the location of the plume changes this dynamic. So for higher radius plumes, if we move them to the side, we will prevent them from interacting with the slab and therefore getting more subduction. But for the smaller plumes, we want them to start from the middle so that we get the most subduction happening. And increasing the size of the plume definitely speeded up the subduction initiation. So some next steps would be that if plume would help initiate subduction in the models that had very thick lithosphere and very buoyant crust, and see if it would, if having a plume would initiate subduction, and vary the temperature of the plume and seeing how that would change the timing of the subduction. And for our last conclusions, run a really like a full suite of models where we change the temperature, size, and the location of the plume to study how the subduction would change, the timing of the subduction would change, and see the long-term effect of having a plume. So seeing if it would also sink with the slab after a while, after the slab gets cut. So some acknowledgements. Thank you, Professor Dave Stegman and Dr. Sue Sermakar for helping me and supporting me throughout this project. And thank you to CIG for supporting the program through the NSF. And thank you to all the mentors and authorities at CIG and SMOREs participants for the opportunity and support. And thank you all for watching my presentation.
Great job, Hiva. Thank you. And so next up, the last presentation will be from Elena Ehrlich. But again, I'll remind everyone, there will be a chance for questions immediately afterwards. Thank you again, Hiva. And Elena, as soon as you're ready.
Okay. Not opening slide. Okay. So my name is Elena Ehrlich. I am a senior physics major at North Carolina State University. And I worked on this project with Dr. Magali Billen and Dr. Max Rudolph from UC Davis. And the project title is Bayesian Uncertainty Quantification of Subduction Zone Rheology from the Geoid. So the question that we were looking at in this project was whether it's possible to look at geoid data and perform Bayesian inversion to recover rheological parameters describing a subduction zone. So we started off with this great subduction zone model that Dr. Billen made, which is a subduction zone between two oceanic plates. You can see here, it's 4,500 kilometers wide and then 2,890 deep, so it extends down to the core mantle boundary. And this diagram here shows the viscosity structure. And then on this slide, you can see the density structure for the same subduction zone. So this is showing the phase transitions at 440 kilometers and 660 kilometers from olivine to Wadsleyite and then perovskite. So the data that we were looking at in this model, we used aspect is what was used to create the model itself, and then the output data from that we calculated geoid observations. So the idea is these are data points that could hypothetically be observed at the surface, measured for a real subduction zone. So it's showing the geoid anomaly along the surface, starting like a little bit in from the subduction zone, so extending in this region here. And the idea, I'm calling this like a synthetic observed geoid. The idea is that it is a stand-in for geoid observations, but we're using a model here so that we know all of the rheological parameters that went into it. Great, so the viscosity in the subduction zone here is described by the flow law that I have on the screen here, where there's a bunch of different parameters that determine viscosity, including activation energy, temperature, etc. But one of those parameters is this prefactor A, which is just a parameter that is entered into aspect. So in various regions in the subduction zone, there are different prefactors describing the viscosity in the different regions. So A0, A1, and A2 represent the parameters for viscosity in the background mantle, and then B0, B1, and B2 represent the prefactors for viscosity in the crust of the subducting plate. So the transitions here are 410 and 660 for the background mantle, and then 80 kilometers and 660 kilometers for the subducting plate crust. And then for the Bayesian Bayesian inversion, the data uncertainty was also treated as an unknown. So for the steps of the Bayesian inversion, we're starting off kind of with the assumption that we know a lot of things about the subduction zone, but we don't know what these viscosity prefactors are. So for the inversion process, you start with just kind of random guesses in a reasonable range of what those prefactor values might be. So here, the prefactor values like used in our initial model, so in the quote unquote observation data, are in red, and then the initial guesses are shown in blue on a logarithmic scale. So this set of initial guesses is the first accepted model for the Bayesian inversion. So we make these guesses and then we calculate the geoid in the same way as we did initially. So we have kind of what we would expect the geoid observations to be for this guess, at an accepted model, and we compare it to what the synthetic observation data was. And we can quantify the misfit between these two sets of geoid observations as a residual sum. And then the next step in the inversion process is to try and take a step closer to the actual solution. So you randomly choose one of those prefactors or the uncertainty for the data and randomly choose an amount to perturb it by, where the probability of taking a step of like various sizes is shown by this bell curve here, where the standard deviation is 0.05. And we're taking the steps in log space as well. So after choosing this new value for the prefactor, this is our new proposed model, which is exactly the same as the previous one, described by that set of prefactors, but one of them has changed. And then what we do is we need to kind of determine if the new model or the old model is better. So the Metropolis-Hastings criterion represents the ratio of probabilities that each of those two models that we're comparing is true. And it can be calculated based on the standard deviation of what the previous accepted model is and the new proposed model is, and then also the residuals for both of those models. And then you randomly sample a uniform distribution with standard deviation of 1, and that is compared to this probability of acceptance to determine whether we accept the new model or we keep the old model. So then you take step after step of choosing one parameter to change at a time and choosing whether to keep the new proposed changes or reject them based on those probabilities. So the idea is that every step you get a little bit closer to what the correct values are. So this is showing the residuals versus the step number. And you can see this took tens of thousands of steps to converge because there are 7 unknowns. So there's like a lot of little tiny steps that we have to take to try and get to the correct solution. But yeah, it's converged once the residual can't go down anymore. So it's as close as it can get to the actual solution within kind of the bounds of the step size that we're taking. And then after that, in the Bayesian inversion process, you have convergence. So you have a sample space with really low misfit, and then you generate a solution ensemble by randomly sampling solutions after that point of convergence. So you have a set of a whole bunch of solutions that all have low misfit. And this is the results. So as you can see, the ensemble solutions end up getting really, really close to the accepted values. So the values that we used to create that uncertainty, or sorry, not that uncertainty, the values that we used to create the synthetic observation data. So yeah, within that 0.05 step in log space, we get really, really close to what the original values were. Yeah, so the question was whether we could take the geoid data and figure out what those viscosity prefactor values were, and we were able to do that with this inversion. But one unrealistic thing about what we did here is there is no noise in the observation data, where if you were actually taking observations of the geoid, there would be more uncertainty. Where here, this is pretty much like perfect observation data because we just calculated it based on that aspect data. So we would want to add some noise to create a more realistic set of geoid observations, and then see how close we can get to those values with more uncertainty in the data. And then we can also investigate other rheological parameters. So those are a couple of steps that we could go to further this research. Yeah, and I just want to say thank you to Dr. Max Rudolph and Dr. Mohammadzadeh for supporting me as mentors, Dr. Lorraine Wong and Dr. John Nalboff for organizing the SMOREs program, the NSF for funding SMOREs, and UC Davis for access to computing resources. And those are my references. Thanks.
Excellent. Well done, Elena. And I want to make a few quick announcements before we get to questions. But first, a round of applause for all the students for the excellent presentations, and really well done, everyone, on a successful summer of research. It's incredible how much all of you accomplished. So well done, everyone, getting to this point. And before we get into the questions, I just want to make a few quick announcements. And it's namely that CIG as a group has not decided what we are going to do for 2022. If we're going to hold the 2020, the SMOREs program in 2022, we are considering it. But at this point, if we do run the program, we would potentially be looking for a lead for the program next summer and also new mentors. Eventually, we'd like to extend the area to more areas of the geodynamics community. So this program is largely about looking at mantle convection and long-term tectonics. We would love to expand it to areas looking at short-term crustal deformation, seismology, the geodynamo, basically all areas of geodynamics. And what we are also considering doing long-term is writing a specific NSF REU grant that would build on the SMOREs program and include a much larger number of students. And we'd also like to integrate that eventually with annual recurring CIG community tutorials, which were sort of interrupted over the last year due to COVID. But with that said, what I'd like to do now is provide the floor to everyone who has questions for the students at this point. And feel free to ask those directly by unmuting yourself or ask them in the chat. Well, while everyone is thinking of their questions, I'll start off with a question. Elena, I was curious, so what rheological parameters would you like to explore next? You're mainly looking at the prefactor, term. Are you thinking about looking at other rheological terms in the viscosity equations, or are you thinking about looking at some of the plasticity parameters next?
Yeah, so I don't know a lot about the other parameters, but I do know that there were a bunch of other factors that went into the making of the model. And the parameters that I was looking at were specific to viscous flow. So I think that your question kind of includes the answer I would give. Yeah, some other types of flow that are included.
Excellent. Really interested to see the results of that. This is the first time I've seen this kind of inversion approach. It's super interesting to see the results of that. Other questions from the audience?
I was wondering, this is a question for Hiva, whether or not there was consideration of maybe changing the shape of the plume. The plume as modeled now is spherical. So is there, what type of changes would you anticipate if you changed both the shape of that and also making it more of an active source, I guess?
Yeah, I think so. There are a lot of people working on this project at UC San Diego. So I know that there is Madeline who is working on slabs that are like oval shape and plumes that are oval shaped. So yeah, so I know that that is happening, and yeah, I think eventually we would like it to look like a potential volcano. So maybe like a circle that has like a top that's not like straight. So yeah, those would be potentials, I think.
And if no one else is, at least for the moment, going to ask a question, I was hoping to ask Kenny a question. And so Kenny, I was specifically wondering, I know you and Joyce have considered running your own 3D convection models going forward. Specifically, what's different parameters or conditions in those 3D models were you thinking about changing from the ones run in STAG YY from the Colty's paper?
I think, yeah, I'd have to look more into like that surface velocity variable that I was talking about in the presentation, but I would do pretty much everything the same except for that radiogenic heating variable, and just kind of see like how that functions throughout time. But since I'm not, there's no like time machine, I'm not sure how it would function, but it's worth a shot trying to see like, I guess, how that would function in earlier.
No. Yeah, I agree. It would be really interesting to see how much that affects things. Other questions from the audience? Okay, well, if there are no further questions, I'd like to take a moment to thank again the students for all their work over the summer. And then also the mentors who put an incredible amount of work into both advising the students and also putting together virtual tutorial and putting together 2 weeks worth of virtual tutorials for the students. That was an enormous amount of work, and it was a collective effort getting to that point, both in terms of the advising, the instruction, and the organization of the program. So thanks again to everyone. Again, for everyone in the audience, if you are interested in participating in this kind of effort, again, either next year or the following year, and also potentially an NSF RU grant, please contact both myself and Lorraine Huang, and we will get you information as soon as we have a rough idea of the schedule going forward. And so the last thing I would like to note is I'll just share my screen again quickly, and I will let Lorraine and provide some information on the next CIG webinars.
Yeah, just a quick reminder to everybody, we won't have a webinar in November due to Veterans Day, but we will be holding our annual meeting the following week, and it's at 1 p.m. and not our usual webinar time. And then there'll be no webinar in December for AGU, and then that'll be followed up by some presentations from projects that have been sponsored by CIG. So look for that in 2022. We'll learn a little bit more about the ABNY project, about the Rayleigh improvements to the Rayleigh source code, and some updates to pilots.
Excellent. Well, that's, I believe, all we have now, unless there are any other announcements. Well, if not, thank you again for joining, everyone. And one last note, I'll be looking forward to seeing some of the student presentations at AGU this year as well.
Great. Thank you, everybody. Thanks to the students. Thanks to Mentor. This has been an incredible program. And thank you for willing to take part in this adventure with us in our first year.